Okay, just a last word. Back to the original set of conditions for conservative or non-conservative forces. Conservative force is path independent. The integral Lagrange of a closed path is always 0. We've addressed these ideas. The curl is 0, curl being del cross F. We've addressed that, at least intuitively and with the rule for calculating the curl. Also, the force, I said, was the derivative of a potential function. The gradient is a generalization of the derivative. It's a rate of change in, well, it gives you the directional derivative, it gives you the direction of maximum change and the rate of maximum change as you move in some direction in space. Okay, in any case, the gradient is a generalization of the derivative, so I replaced the word derivative with gradient. I kind of think your book used the word derivative. I've used the word gradient, but I know your book talks about the gradient, so I could be wrong about that. Okay, now, if f equals g of x times I, then what can we say about potential functions and so forth? Well, I had the phi here. I called this function phi. Now, phi is the standard notation that you would use for an electrostatic field, the potential, electrostatic potential. And you even apply it sometimes to magnetic potentials, but that's a little different. Okay, so I used phi just out of reflex, but if we want to use the notation of the book for a potential energy field, we can use U. So my point is, if f of x equals g of x times I, then if u prime of x equals g of x, then f of x equals u prime of x times I. That's a simple substitution. If u prime of x equals g of x, we put g of x in here and we get this. Okay? So that's really a no-brainer type of statement, but of course you have to digest it before you see that. Question is then, what is u of x? Well, I said we were going to finish that later, but I can finish it now. U of x is an integral of your g of x function. I mean, if u prime of x equals g of x, then u of x is an integral of g of x. That's your fundamental theorem of calculus. Okay, now, it follows that if g of x is an integrable function of x, then this field has to be conservative. Because if g of x is integrable, then you can do this integral and get your potential function. Okay, now what about f of x equals g of y times I, or even h of yz times I? Remember what happened when we just let f of x equals y times I. We found that the integral around that square was no longer 0. We found that the circulation around that square was non-zero, so that this function is not conservative. You can also show that if you try to find a potential function for this function using the same attempt that we made, same type of attempt we made when this was just y times I, with the g of y, the argument doesn't change much. Now, you should try to work through that, especially if you have time and interest. You might wait until you're done with the multivariable calculus course, in which case you'll be a little more experienced with this sort of thing. On the other hand, doing this now, if you can do it, is going to give you a leg up in your multivariable calculus course if you happen to be taking it. And if you don't happen to be taking it, you don't really even have to worry about all this stuff anyway. Just take my word for it all. Okay? And the same thing if h is a function of y and z. As long as the coefficient function of I has no x dependence, but it has a y and a z dependence, y and or a z dependence, you're not going to be able to derive a potential function. You're going to end up with a contradiction. Okay, that should do it for today. Also mention if you have questions about any tests that you see, get them to me. I'm going to try to address a couple of those before I fall over from lack of food. Okay.